Hi everyone, this is the third video in the Introduction to Vector Operations and the Projective Plane. We've gone over the dot product and the determinant, and now we're going to start looking at the cross product and how it fits in with the determinant and why it looks the weird way it does with the ijk on top and then the two vectors, and also we're going to prove that the vector that it gives us is in fact normal to the plane and the magnitude of the area of the parallelogram. So first up is just exploring why it looks the way it does.
Okay, now the cross product, the last one of the vector sort of operations. So what we're really talking about is the dot product and the determinant. The dot product measures when you multiply, in some sense, the same components together, and the determinant gives you when you multiply the opposite components or the different components. So you end up with a volume or an area instead of a magnitude. So the cross product relates to just the three-dimensional determinant, basically. So we were looking at the three-dimensional determinant, and okay, so we have A here, this is B, and this is C. So we're looking at the volume of this parallelepiped. And we already know that the determinant, or I'm going to show you that the determinant, the 3D determinant will give you the volume of this. But the question is, what is the cross product? Because remember, the cross product is the very strange animal I, J, K, and then A1, A2, A3, B1, B2, B3. And the question is, why? What does that have to do with anything, and how does it help? So that's what I'm going to show you. It's not, the cross product, it isn't really a thing on its own. It is sort of everything that's left in order to find the volume of this. And I'll show you what that means in a minute. But basically, it's just a construct that fills in the information that we need in order to get the volume of three vectors in 3D space. So again, the volume of this is just the area of the base times the height, right? Basically, area volume, it's always the area of the base times the perpendicular height. So in this case, just like if you remember with a parallelogram, we had A, B, and we dropped down a height here. Here, it's the base times the height. It's always the base times the height, the base times the height. So in 2 dimensions, it's the base times the height. In 3 dimensions, the base is the area times the height. So here, to find the area of this was the base times the height, that was the length of A, times the length of B times the sine of this angle. And that was because the sine of this angle is the opposite over the hypotenuse. So if you move that over, so if we have the sine of theta equals the opposite over the hypotenuse, then the height is the base is B times the sine of theta, okay? So for the volume, we're doing the same thing. We want the area of this times, we have this angle here, and we need to do it exactly the same way. We have this triangle here. This is a right triangle with this C is the hypotenuse and H is the value that we want. So we have again that the height, just like here, the height is the length of the hypotenuse times the sine of this angle. So the volume then, if we plug that in here, the volume of the parallelepiped is V equals the area of the base, and I'm just going to call that area, times, and then we have to get to the height, and we get that by the length of C times the sine of the angle B. So the length of C times the sine of this angle, theta. Okay? So that is virtually identical to the area equation, right? We had the base times the hypotenuse times sine theta. Here we have the base again, which in this case is the area, times the hypotenuse again, which is C, times the sine of the angle theta. And then remember, how did we actually calculate this? We did this by taking the instead of looking at the sine of this angle, we can do the same thing we did with the determinant. We can take a perpendicular angle to the base, and then take the cosine of this angle in order to get h. So height here is also the length of C times the cosine of this angle instead of times the sine of this angle. Those are the same. So if we do that, in other words, the volume would also be, if we make this vector basically the length of the value of the area times C times cosine of this angle here. Okay, this is exactly what we did with the determinant, where you have the sine, you take the perpendicular of the base and multiply that by the cosine, and then that looks just like the dot product. So this looks just like a dot product, right? The definition, or not the definition, but we can, one way to look at the dot product is the length of A times the length of B times the cosine of the angle between them. That's exactly what we have here. But in this case, instead of two angles, we have some vector that represents the area of this perpendicular to the base that we want. So here's the base, and we want a vector that's perpendicular to that base, which we're then going to multiply by C times the cosine of theta. So what we have then, this represents the dot product between A and B. So if we just imagine that we have a vector perpendicular to the area, to the base, with a length that's equal to the area, and then we take the dot product of it with C, that is what we have here. So in some way, so we have something dotted with C will give us the volume. And what is this? This is a vector perpendicular to the base with a length, with a magnitude equal the area of the base. Okay? So I'm just going to call that A cross B. Okay? So we don't know what this is yet, But we know what it represents. It represents a vector, or they say it's a pseudo-vector, perpendicular to the base, which has a magnitude that's the area of the base. So if you take that vector and you dot it times the c up here, you're going to end up with the volume of this parallelepiped. So now the question is still, what is this? We've named it, but now we have to look at how we get that value. So this is what I mean when I say that the cross product, it isn't a thing in any natural way. What it is what's left over in this equation. We want something dotted with c to give us the volume. That something is a perpendicular vector with the magnitude that's the area of the base. That's what this is. Now, how do we do that? That's what we're going to look at now. So remember, we're saying that the determinant, the 3D determinant, will give you the volume. So volume equals so we have A, B, C. Why am I getting confused here? There. So if we take the determinant of these three, so we have that A equals A1, A2, A3, B equals B1, B2, B3, C equals C1. So again, this is going to be the volume for the reasons that we talked about before. So this is what we want to equal something dotted with C equals the volume, right? So this determinant equals something dotted with C. So we know that the 3 by 3 determinant, if we calculate this, it's always the minor determinants times the other one, plus the minor determinant plus the other one, or times the other one, plus the minor determinant times the other one. So the determinant of that one equals C1, oops. So it equals the minor determinant, A2, B3, minus A3, B2 times C1, plus A3, B1, minus A1, B3, C2, plus A1, B2, minus A2, B1, C3. So this is the volume. Now, remember what we want to do here is dot something times C. Well, you can see this is a dot product, right? It's something times the first component plus something times the second component times something times the third component. So this is basically, if you look at this as a vector with these three components and you dotted that with C, you'll get the volume. That's what we want. So what is this? This then would be a vector with components This vector dotted with this vector gives us the volume. This vector then is a vector that's perpendicular to the base and has a magnitude equal to the area. That's this vector. And we can see that what we ended up with there was then, this is also clearly the determinant, right? With I, j, and k instead of c, c1, c2, c3. So this is also I, j, k right? Here we have the determinant with c, a, and b. Here we have the determinant of I, j, and k with a and b. So you can see they're the same except for the c's instead of the j's. That's what dotting by the c does. Okay, that all looks good, but we still haven't actually proven anything yet. I'm just showing you that this determinant fits in here, but I haven't shown you that in fact this is a vector perpendicular to the base and the magnitude of the area of A. We still don't know that that's true. So I have to show you two things. First of all, that let's call this vector, well, let's call it A cross B. First of all, that vector is normal, meaning perpendicular, to the base AB, meaning here, and two, that vector has a magnitude equal to the area. Up here. So we still have to show those two things. That's what we're going to do now. Because then we end up with this, and then we can see this is the cross product, right? With I, j, and k, and you take the determinant of this thing, and you end up with this, which times the c will be the volume. But we need to show that these in fact equal, that it's normal, and that it has a magnitude equal to the area.
Okay, we're going to stop this video here. So we still have two things left to do. We need to prove that the vector that the cross product gives us is normal to the parallelogram, and secondly, that its magnitude equals the area of the parallelogram. So the next video will be proving that the vector is normal, and then the next one after that will be will show us that the magnitude is equal to the area. And then we'll move on to the equation of plane, and then finally, with all that information, we'll be ready to look at the projective plane and homogeneous coordinates. Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.